Hello everybody. My name is Jens Müller. I'm a Master of Science student at the University of Bochum, free software developer once in a time, and currently into weblog forensics. As the title may be a bit misleading, this talk is basically about an introduction about the art of gathering important information from weblog files. Important in this case means attacks. We will briefly discuss various techniques to find attacks against web applications, also the web server, but more web applications, which is essentially signature-based and learning-based approaches. Afterwards, we'll try to characterize these attacks in terms of who did something and what exactly was done. Who, in this case, refers to the attacker, like is he coming from Switzerland? Is he part of some botnet? Or is he a machine, some script, or is he a human being trying to get into my machine? What refers to the attack itself, meaning in terms of severity of the attack. So we are trying to at least distinguish between successful and non-successful attacks. Everything shown in this talk has been implemented in some prototype, so you can test it with your very own access logs afterwards if you're curious. So here's our scenario. We or some customer or whoever, some website got hacked, got owned. Sometimes they leave pretty cool ASCII art behind. In other cases, they try to steal our very private data, and we find it in the internet, which then is maybe less good. In any case, probably some web application was insecure, and now we are interested in how they did it. We should be, else if we just reset our servers, we will just get owned again next week. So what do? We make an image of the disk. We look for suspicious files, for backdoors and so on. We search for unusual activity in the log files. Since we, of course, didn't use mod security and audit logging, we only have just basic Apache or on Ging, so whatever access logs, which is a very common scenario for post-log forensics. But for some reason, luckily, we think that the log files have not been manipulated because they were stored on a separate machine with crypto and append only, and we think the log files are fine and integer. So we think we have pretty good chances to understand what happened or not. Well, the basic problem is with log files that they are pretty huge. And by huge, I mean they can get really, really huge, and we are kind of lazy, and at least we don't have a motivation to manually review terabytes of log file data. So remember, the attack could have happened weeks ago, and the defacement is now, so we might really have to look through all those data. We have some great Unix tools out there like Gradset, org, and how they're all called. But maybe we want to use something that was more especially designed for the job of finding attacks or suspicious activity in web logs. Why not using a tool designed for the job? Because we simply have none, or not in the open source field at least. So what do we have? Here's a market study of mostly open source stuff. We have got some really good web application firewalls and intrusion detection systems on that layer. Mod security does a really good job. We have OWASP App Sensor Framework. We have PHP IDS for PHP-based web applications. And then we have a bunch of commercial web application firewalls out there. This is more on the network level, and then on the log level, we have kind of many tools for analytics, monitoring, and forensics. which then can work, like Pivot can work on the log files, does not have to necessarily. WebAlyzer or HW stats are designed for this, for web analytics. GoAccess is a cool program for the console. We have Splunk and pflags, which to work on any kind of logs, and you can really do good analytics there. Go into detail, sort for certain fields, look for bursts. So they're designed for forensics, but they are not especially for web stuff. So it's more like outliers in any kind of data, but they don't. We have some special needs for web logs. So the idea is, why not just combine both worlds, create a tool that is based on log data but uses the algorithms from the world of web application firewalls. The only tool I'm aware of is Sculpt, which basically uses the filter file of PHP IDS, then matches the requests against the filters and marks it as an attack with a certain severity. This is a good start, but it does not make use of request normalization as provided by PHP IDS, and so I just tested it yesterday. A simple URL encoding will leave the attack undetected. So, and that's the only tool, at least I'm aware of, in the open source world. So we might be, we sort of created something a little bit more advanced. So here's a typical weblog file in the common format, which is used by Apache and others by default. As you can see here, one of the values of the URL query string parameter called page is somewhat different, the red one, meaning an attacker is trying to include our password file instead of a regular page. So this is just a simple example for local file inclusion. Yet here's some more. So you're probably all familiar with. We can maybe execute or include even remote files, execute commands if there was some logical programming error in the web application, get access to the database, do cross-site scripting, or maybe less common these days, do buffer overflows, exploit buffer overflows, and there's many more. This is just to give you some short understanding of what different kinds of input approach detection technique would have to be capable of handling. So, as always, there's two approaches, which is signature-based and learning-based. What we implemented is to just use PHP IDS, so a regular expression-based approach, then an approach based on statistics, the length and the character distribution called a chars detection module, and then a machine learning-based detection module, which is based on hidden Markov models called MCS HMM. That's all not new. It's more an implementation task, and we will come to, we'll later see what to do with that. So, as said, there's been a lot of research in the field of detection and prevention of web-based attacks in the past years. We have approaches based on signatures, which back in 2000 then meant just matching for vulnerable CGI scripts. Later on, more complex regular expressions were developed to cover a broader range of attacks. So what we did is just use PHP IDS, pipe every URL query field value through it. So we use the PHP IDS conversation and deobfuscation and normalization process, and then match its outcome against the provided about 70 regular expressions, which try to match for certain kinds of attacks. So in the end, PHP IDS produces us some numerical value as a result, called the impact of the attacks. So we do nothing more than just make use of PHP IDS on log files. As for some really basic statistics, there's been some ideas like have a look at the length. The longer the URL query string is, relatively the more unusual it may be. more maybe an attack. Also, while characters of the Latin alphabet or digits are commonly seen within URL query strings, other characters might be evidence of an attack. There have been approaches based on the character distribution, meaning the relative frequency of characters within URL query string values by very bright people out there. So what we do is just use the idea of the length and the character distribution in a very, very simple way. For all web applications, URL query string parameter values, we calculate the mean of the occurrence of non-alphanumeric characters. We do this by simply removing all digits and Unicode letters, and then we compare it against the mean of non-alphanumeric, meaning special characters for certain URL query string parameter. You say that's too simple, probably. Absolutely it is. But it is pretty fast instead of walking through dozens of regular expressions, and generally if the variance and the mean of special characters for a certain web application are low, then, which is for many web applications true, then we have good chances to use this simple algorithm at least to get a quick overview. Third detection module is based on machine learning. This has been a field of research in the last decade. Many interesting approaches. We have seen approaches based on bias parameter estimation, self-organizing maps, DFAs. People have used neural networks, wavelet transformations, n-grams, just to give you an overview. In the last years, hidden Markov models have proven to give very good results for detecting attacks in web traffic or network traffic in general. So what we did is just use an approach that was presented in 2009, implemented, and that's why I'm just shortly, I'm not going into details what hidden Markov models are. This would probably go beyond the talk. So generally it's just a learning-based model where we learn the length of some observations. In this case, this is the values, like we had news, index, wiki, and then etc password ones, and hope to give some prediction about, in this case, the probability of some further observation, like etc password. First of all, what we do is we aggregate the data. We build an ensemble of models. Normally 5 models seems to be a very good value. The more the less good it performs, the less, if we do not take enough models, then our results are not that good. We do this for every URL query string parameter for every web application just defined by path, so every web application that is on our server. We convert the values, the alphabetic values to an A and the numerical values to an N. This is to get better results because this changes very often, and if it changes, it gets less usual. But we think that attacks hopefully are not carried out by only alphanumeric characters. We train the models using the Baum-Welch algorithm, and then test certain value like etc password, certain observation using the Witherby algorithm. So it's probably if it's a non-malicious value that we get as a return. In the end, we apply a multi-classification system and just take the model with the highest probability to get less false positives, and in the end, the best result. As said, this is totally nothing new, and it's more an implementation idea. And so we did some evaluation. We used the training data of our institute's web server. It's 3 weeks logs, 60,000 requests altogether, 40,000 a day. All incoming traffic has been pre-filtered by some firewall with IPS. So we think that most of the attacks didn't even get to the logs. which is good because we wanted an attack-free or mostly attack-free training data set. We need this, if possible, an unpoisoned data set, and it's okay to use this in the terms of just measuring our false positive rate. As test data, we used 40 real-world exploits from various sources like Milgram, or what's it called now, 9 command execution, local file inclusion, cross-site scripting, cross-site request forgery, and 13 SQL injection. The payloads were just placed in the values of normal web applications. The only thing was we only used HTTP GET because we simply don't see post data in the logs. This is a major drawback. We'll come to that later. If an attack is carried out by post, mostly we won't see it in normal access logs. So here's the result. As you can see, the hidden Markov models do give the best detection results. Generally, they are also the slowest. It even detected 100% of, so the 0 is 0% and the 1 on the epsilon axis is 100% of the true positives, but with an intolerable false positive rate of 1%. So you would probably choose a threshold in the upper left corner somewhere to get best results in the end. The character distribution in this case was very well, even better than PHP-ADS, but this is because the dataset did not contain that many different values. So if the variance of the values is not that big, if you do not have that many special characters normally, then this module can give good results. It's also normally the fastest. As for PHP-IDS, that's just a rock-solid module to use because it's independent of the training data, so it gives the same result even if it's just one request, while the statistics, they need several values. The learning-based algorithms do even need more training data to work on, so PHP-IDS is just a rock-solid choice. So now we have those detection algorithms, and they have completed, but we still have thousands of lines of potential attacks, which is too much data still and too less information. So what we can do is get information about the attacker a little bit more, and even more interesting, maybe get information about the attack. For the attacker, we can group his activities into sessions and then try to see if it's been a human being or some machine, some script. We can also do a geomapping or look up if it came from some botnet maybe, because it might be interesting. Then we can try to evaluate if an attack was successful or not, because we don't care about unsuccessful attacks normally. So we try to add the missing context here. Well, as for session identification, it's just based on inter-request time delay and change of user agent. And then after we have several sessions, we say random scan if it's just one single request of some worm or something we probably do not care if we do not have especially that vulnerability on our server. A targeted attack might be a bit more dangerous because somebody's running some scripts or so, but don't know. A human attacker is probably the most dangerous kind of attack because it means that a real human being is trying to get into our web server. Also, it's interesting that often the flow is that people first run automated scans and then later come back as human beings and try to look if the results of the scans really do manual probing and try to get in them. The algorithms are just stolen from robot detection techniques. pretty easy. By default, we say it's a human attacker. If there's only one request, we say it's some random worm thing, whatever. If the robots.txt file is requested, then it might be a machine. Of course, a human can do that too. If it's non-get post requests, the same. Also, of course, it could be a human with some program. If the average time delay for web applications, meaning not images, which is identified by the file extension, is less than 1 second, then we think, well, nobody can click that fast. If the total number of web applications is greater than 1,000, well, maybe that's a machine too. And if the code of HTTP response codes that are in the 400 sector, like 404, is greater than a dynamic threshold, then it might be a machine too, because we use a dynamic threshold because we think that a human being might learn. If you always get 404, you won't click on, and the machine will just try and try and try for web applications that don't exist. So next we can gather some more information about the attacker. We can do some geomapping. This was a miserably failed idea where I thought it's the weblogs of some local company near Cologne, and I applied a density-based outlier algorithm, and the idea was that it might be unusual if the request doesn't come from a certain hotspot of activity. It was a totally dumb idea, and it's totally discriminating against people originating from Greece in this case. So let's forget about that. But it's still interesting to somehow know where the attacks come from on a geographical level. Then what we also can do is just add some DNS black hole list information. We do this by requesting several lists, like a Barracuda Central or whatever. Several lists are made for several kinds of like spam, so that we know the IP address has already probably been at least suspicious of spamming. That's not too interesting. Interesting maybe if it's part of a botnet. Interesting maybe if the attacker uses some open HTTP or SOX proxies. Also interesting is if the attack is carried out by the Tor network. Please don't sue Tor network operators. They are doing a great job in defending us from prison and what all the surveillance programs are called, and please don't do that. So for us, does yet another unsuccessful scan matter? Depending on your network setup, if you are connected to the internet, then probably no, because you will have this every couple of minutes. So it would be interesting to know if the attacker succeeded. So what does succeed mean in this case? We need to somehow define this. Is it just information disclosure, like the path of the web application, or is it a file disclosure, like some data is leaked, or is it the compromise of the server, or is it a hacked account? So this kind of depends on your setup and on your security level. What we now do is we just replay the attacks for every single request identified as attack. We replay it, we match for certain signatures, and then think, oh, that might be some info leaking or file leaking. We match for the parser file, for example. This is just an excerpt for some source code files. As are private keys. We can match for error messages, PHP, Java, Python, whatever, if this is important for us, or if some file path is leaked, some database message is leaked. Yeah, we can do that. But isn't that kind of too easy? In many cases, the web server isn't up anymore. If it is, we might even change its contents by replaying the attacks. Maybe we want to evaluate the success of attacks with only the log file information, as you can see there. So how to do this? Has anybody any idea? That's a very good idea. First, I thought about the HTTP response code, but that does really not make sense for web applications anymore. Maybe it made sense for HTTP access or something like that for HT access. But unsuccessful login for web applications always 200. We always just get 200. So we still don't know if the etc password is included or not. So as you just said, what we do is we look at the byte sent value. Even though we don't know, we have no access to the actual response, we do have the field which is the bytes sent. Okay. What we can see from HTTP response codes is maybe 404, we can at least say, wow, okay, they looked for some web app and it didn't exist, and we can maybe exclude that. But we can't learn much more from response codes. So as for the byte sent value, we can look for outliers in there and then say, oh, if there's an outlier, then the actual content of the response is different than normally, and then it might be interesting. Problem is that we don't have normally or very often a static content with always the same byte sent value, and then we get something else, and then we know it's an outlier. So we often have, like in the example, we have page, news, blog, index, and so on. They have all some dynamic content. So, but we still can see there's some hotspot in some magnitude of value. We also can maybe have several hotspots. That's why we used a density-based outlier algorithm, the local outlier factor, which is pretty slow, but okay. Because we do this only for requests detected as attacks. So this is highly experimental. It still produces a very high false positive rate. Yeah, but it in the test it kind of worked. So as you can see, the etc password is 2,219 bytes. If that is the size of our password file, then we have got a problem now. The wiki might also be an outlier, but with some thresholding, you might be able to handle this. In the end, you probably have to manually still check it. Oh, as I just had to reboot. Yeah, I wanted to show you some examples of the program. This is some personal notes, just ignore that. Now we have some JavaScript that takes some time. So here we go. As we can see, this is some example of some real-world log file. We have some timeline of the attacks up there. We have certain colors for the impact. We can maybe search for certain strings, like a password, and then have a look. Okay, somebody tried to include the password file. It's 404, so we don't care. We can sort by client, by their impact, by some kind of attack classification made by PHP IDS, but yeah, that's not too clear. We can say we only want status code 200, which might be more interested because we don't care about all the, as said, 400 error codes. And we can also say, let's just let's just have a look at the attacks originating from botnets or from Tor servers and people who have been spammed already. So things like that we can sort by the request method. What we also can see in this kind of visualization very good is that, for example, you can very often see it's over there 20, 45, 20, and so on. That's all the same script which scans for AW stats, AW stats, which you can easily see in this map kind of visualization. Then I hope it works. We have another kind of more what you would give for some automatically generated report. I hope you can read it. For example, this host is a random scan last year from I don't know where. No, we don't know because the attacker covered his identity because it comes from botnet, so don't even try tracking. It says it has got some severity. I don't think that's true in this case. Just give me a second. So this is our data set of the institution, and we included some files of the. This is the experimental attacks with the etc password or whatever included. So the byte send value has been set to the corresponding value if the attack would be successful, and in many cases it just detected it by some kind of outlier factor. Oh, that's not good. Totally not good. So maybe we can look at those ones. That's also a real world example, which is also interesting because we can see it's, I hope you can read it, it's a targeted scan and then later on a human attacker. And here we can see which web applications were mostly targeted. And here also we have some probably SQL injection. It doesn't. I didn't. You can automatically say URL encoding and deobfuscation. This wasn't enabled in this case. So, anyways, this is some example. Here's more for some tool called SQL.php, and we don't know if that's a legitimate tool on our server, but yeah. Also, we can see if an attack was carried out by day or night, which is like this one. So it might be interesting if in the certain time zone the attack was carried out maybe from midnight to 8 o'clock, because then it probably was some hacker and not some government guy, because they work from 8 to 5, and yeah, maybe that might be interesting. So okay, this is just some experiments with visualization. You can also get it as some CSV data or JSON or XML or whatever the produced output. So yeah, I think that's almost the last slide. Let's just briefly discuss some countermeasures of an attacker to evade detection. For all the learning-based algorithms, clearly, if an attacker can write to the training data and poison large portions of it, we have just simply lost. The same is for statistics. In the worst case, he can make normal requests look like identified as attacks and the other way around. So that's a real problem. We need not total 100% clean training data, but 90% or at least large portions of the training data should be regular requests, else all learning and statistic-based approaches will fail. So what we did to countermeasure this is that we just learn until we have enough examples and then stop learning. So it's also a performance issue. And we only learn from, let's say, 100 different IP addresses. So that's still not perfect, but an attacker has to have access to very many IP addresses, and he has to poison the training data at the very beginning to make his attacks undetected. Another countermeasure maybe would be a hybrid approach and just run PHP IDS to filter out large portions and then afterwards run a learning-based approach. What else can an attacker do? There's so many ways of payload obfuscation in the web, like URL encoding or hundreds of ways to obfuscate evil JavaScript. One countermeasure is to just use the PHP IDS conversion engine for all detection modules and then hope that the obfuscation is correctly applied. Then another problem is that an attacker can use vectors that are simply not logged or not visible to us. This is a real problem. We usually don't have access to post data, as said, or to any parts of the HTTP body or header. So just carrying out your attack with post instead of get will simply be an effective way to evade detection in forensics later. And the Apache developers don't really make it too easy to log post data. So then we have some attacks that are just not visible to the server because it's never ever transmitted there, like DOM-based cross-site scripting. What also can be done is try to hide the flow of the attack, the course of events in separate steps, so slowing down the attack in time or carrying out from many multiple origins to hide that all the steps are part of one and the same prechain. On the other hand, we can also create just a fluid of nonsense attacks, maybe hundreds of thousands, and making the detection modules trigger, but then making it difficult for them to see which attack is the real attack, the attack that was meant to be successful, because it's still difficult to see, to distinguish between successful and non-successful attacks. Then on the log file-based side, what an attacker can do is do attacks against the logging itself. Obviously, if he's got root or somehow write access to the log files, he can remove any evidence of his behavior. Clearly, what we do is we run a simple grubs outlier test against the log files inter-request time delays. So we can detect at least large-scale truncation within the log data. But those outliers can also caused by natural phenomena, normal phenomena like temporarily disabled log services, network downtimes, some clock changes, or no company access at Christmas. So, and still if we detect that the log file has been manipulated, we don't gain anything of that. So always store your log files on a safe place. Maybe a separate machine. So what we also can do is maybe a denial of service, that separate machine that takes the logs and saves them. So we can somehow denial of service the log server. Or we can send one byte to an old version of Apache and then it will simply stop logging, but this is fixed since years. Last but not least, an attacker can do log fluting by just sending really many requests. So our disks are not infinite, and in the end, we will at some point reach the end of the disk, can no longer log, then the attack is carried out. I don't know if it's too practical, but maybe at least something to think about. If we have log rotation that is based on file sizes, then we could carry out the attack and afterwards make a much of normal requests, and then by rotation the attack might get overwritten. So maybe that's something to think about for forensics. So, thanks for your attention. I hope you enjoyed the talk. All source code and research and this presentation is online at GitHub. One warning, the implementation is still pretty much pre-alpha code. There are bugs inside. They are probably exploitable by specially crafted log files. So maybe it's your homework to try this out. Also, if you think that's an interesting project, feel free to join or to fork or just talk to me later at a beer. So I think we have time for one question, two, I don't know. Any questions?
Hello, thank you for your talk. I find it quite interesting, but so there are still some work to do, it seems, and that's quite interesting. So you said there are some cases in which payloads are not visible, such as the DOM-based XSS, and I thought, like, since you're trying to find actual successful attacks, so if we take, for example, CSRF attacks, is there a way that your log, as you call it, can detect CSRF?
I'm not sure if I got the question correctly, but what was meant was that if the attack is only against the client, then if we can't see it from the server side, then we have no chance in detecting it.
Yes, that's what I understood. Okay, thank you.
Thanks for the talk. At first, a bit about the background. I work for a company which operates an ISP free mail service with about 50 million customers. And you can imagine that we generate a lot of log data. And we always have the problem that we need a software who is able to work with this large amount of data. Do you have any number how your software performs on enormous amounts of data?
Not too well. So it's if you have got hundreds of megabytes, it's still in, depending on the algorithm, it can be in some minutes, but if it's more, then you're getting into trouble. Well, if somebody wants to help improve the algorithms, you're free, it's an open source project. I'd maybe use Splunk for this, which is not really designed for the job, but you could give it a try because it works really fast on large log data.
Thanks.
So then, thank you.